Hello, welcome to Maths with EJD. Still talking about numerical analysis and partial differential equations in particular. That's not numerical solutions to partial differential equations. We have seen methods like finite difference method, finite element method, and spectral methods for solving partial differential equations. So this video is meant to compare how the three of them go. Number one, we have the finite difference method, which is FDM for short. First of all, we talk about the approach. Okay. So finite difference method, FDM, discretizes the domain into a grid and approximates derivatives using finite differences. So that's the approach for finite difference method. Now, talking about the strengths now. Strengths. One big strength of FDM is that it is simple to implement for regular grids. So if the grids are regular, then it's simple to implement, especially for problems with uniform boundary conditions. And what can we consider the weaknesses of the finite difference method? Weaknesses. So it is less accurate. It is less accurate for irregular domains. And complex boundary conditions. And complex boundary conditions. It is also limited in flexibility, so it has limited flexibility. Okay, that's about finite difference method. Now let's consider the finite element method. Two, finite element method. FEM. FEM. So first of all, the approach. Finite element method divides the domain into elements and approximates solutions using piecewise polynomial functions. Using piecewise polynomial functions often used. It's often used for irregular geometries. Irregular geometries. So, if you have something like a cube, a cuboid, and all that, that is regular. But if it is irregular and it is shapeless, then you can now divide that shapeless thing into smaller elements, depending on the dimension you're working in. So it's often used for irregular geometries. And then we talk about the strengths of the finite element method. The strength, the strength is that it is highly flexible. It's highly flexible. Okay. works well. It works well for complex geometries. So in this regard, it's better than the finite difference method, which cannot cope with irregular geometry. So this works well for complex geometries and complex boundary conditions. Complex geometries and boundary conditions. Then we also have that, yeah, that's it. Then the weaknesses now, the weaknesses of finite element method, weaknesses. So it's more computationally intensive, because you need to divide into several finite elements. Then two, it requires sophisticated meshing. Unlike the finite difference method, which is just you just discretize and then you go on. So that takes us to the third method, which is the spectral method. Spectral method, or you can say spectral methods, because you need basis functions that can be Fourier, Legendre, Chebyshev, and all that. So talk about spectral method now. So the approach, it expands the solutions, as a sum of global basis, the sum of global basis functions, e.g., Fourier or Chebyshev polynomials. Okay, that's the approach. Expand solutions as a sum of global basis functions. What about the strengths? So the strength here is that it has very high accuracy for smooth problems, especially in problems with periodic or smooth boundary conditions. Then the weaknesses of the spectral methods, it struggles with irregular domains. It struggles with irregular domains or discontinuities. So once the function is not smooth, it doesn't work too well. Irregular domains or discontinuities. Another point is that it is complex to implement. I mean, if you refer to the video, you discover I was just going on endlessly. But I mean, thank God for coding that makes it a bit easier. So it is complex to implement. So all we are saying in summary is that in summary, finite difference method is a straightforward, and good. Oh, finite difference method is straightforward, right? So it's straightforward now. Finite difference method is straightforward and good for regular grids. 2, finite element method excels in handling complex geometries, especially because it breaks down the geometries into finite elements. Then lastly, spectral methods. Spectral methods offer superior accuracy for smooth solutions, but are less flexible with irregularities. Okay, so that goes. Yeah, to round off this comparison between finite difference methods and finite element method and spectral methods, um, let's revisit the heat equation, the one-dimensional heat equation, and see how each of these methods implements the heat equation. So for the finite difference method, right, you know, we have the length of, imagine a rod of length 1 meter or whatever, or 1 kilometer, anything you want to call it. Then you have the the total time it's taken is 0.5, say minutes or seconds or whatever we want to say. Then we have number of spatial points 10, number of time points 100. Alpha is 0.01. That's the time of diffusivity. Then dx is L over n, and nx minus, that's spatial step size. dt is time step size and all that. And if we implement this for the heat equation, so it gives us something like this for the different time steps, like that. And then we have finite elements method here now, the same length and all that. Then same everything except for how the implementation is carried out, which is defined in line 21 to 29, where we talk about the finite difference. Oh, okay, yeah. I'm talking about finite element now. So for the finite element, so same thing, LT, blah blah. Okay, the total time up there was yeah, same total time 0.5. So everything is the same apart from the implementation. Then here we need the stability parameter, which is alpha dt, the x squared for the finite element method. And then, all of this. So the main implementation, we now need to construct the stiffness matrix and mass matrix as sparse matrices. I think that's where we solve Ku equals F or something like that. And by the time we run all this, we get something almost similar with what we got previously. I think, yeah, about almost the same. Yeah, almost the same. I mean, this is a very simple partial differential equation. So when things get complicated, we may not expect to see the same behavior from all the methods. So this is a very basic method. Then here we have spectral method, which is even employing fast Fourier transform, since we are talking about Fourier series as general base function. And if you do this too, you get uh, now you get something a bit more of beauty is added, because of course Fourier function is kind of periodic. It involves sine and all that. So, and that's why this is coming out this way. So that's how that has been. And as far as the comparison is concerned, so when next you have to solve a partial differential equation, think of the nature of the equation. By the time I teach differential equations, right, and we get to partial differential equations, I'm going to really emphasize on the differences like elliptic, hyperbolic, and parabolic partial differential equation. So from the behavior of the equation, you can know which of the the best method to actually apply. Okay. Having said that, if you have subscribed to this channel, thank you so much. If you have not hit the notification bell, though, please you want to do that so that you can always get alerted each time a new video is released. And of course, if you have not subscribed at all, please go ahead and do the same. Subscribe and hit the notification bell. Of course, drop comment. Let me know how helpful these videos are. Let me also know if there's a topic you'd like me to teach or a problem you'd like me to solve. And don't forget to like and share. I mean, in the previous video, in some videos in the past, I've had to give practice questions. So you can also comment, maybe on Facebook or YouTube. Just let me see your efforts, in the comments. So like and share so that more people can also have access to this great learning. So with this, I'm done with partial differential equations. So I think the next thing we'll be talking about will be numerical optimization techniques. So where we talk about things like gradient descent method and all of that. So let's see how far we can go with that. So watch out. You don't want to miss out on any of these things. Bye.